Hi GOH, this is Unit 7, Lesson 4, and today we're going to talk about similarity. So we've seen that when a figure is dilated that all the sides are scaled according to the scaling factor, and the angles are preserved. So that's what we learned in the first couple lessons. In this sense, we say that the two figures have the same shape but different sizes. Two shapes that share such properties are known as similar figures. So here's our definition of similar figures, and that figures are similar, and the symbol that we're going to use for similar is this little like sideways backwards S. Remember when we did congruent, it was the equal sign with that little symbol on top? Well, now similar is just that symbol right there. So two geometric figures are similar if all pairs of corresponding sides are proportional and the corresponding angles are of equal measure. So those are the two things that you need to remember, that the angles are congruent, the sides are in proportion, and that proportion is based on the scale factor. So in the diagram below for exercise 1, we have triangle ABC is similar to triangle DEF. We can see that DEF is definitely bigger, so they are not the same size. But all those angles are congruent. So I'm not going to use tracing paper, but I just want to show you that angle A is congruent to angle D, and see how A is the first letter and D is the first letter? That's telling me what's matching up. Angle B is the second letter. Grab a different color, and that's congruent to angle E. So angle B over here is congruent to angle E. And the last one, I have angle C is congruent to angle F. So these haven't been turned around or anything like that, but if they were, I could use the order of the letters to know what angles were matching up and what was corresponding and which ones were congruent to each other. So now I'm going to solve to find the missing side lengths of both triangles, and I'm going to show my work. Well, since they're similar, their sides are in proportion. So all I'm going to do is make a proportion up. So how about I'll first find EF, and I'll call that X. So what I'm going to do is I'm going to take the two sides from the smaller triangle, and I'm going to take the two corresponding sides from the bigger triangle, and I'm going to write a proportion out. So 7 over 8, and then 14 over x. Now the way that you solve a proportion is you cross multiply. So I cross multiply, 7 times x is 7x, 8 times 14 is 112, and then I divide by 7, and x equals 16. All right, and then if I wanted to find this other side, I'll call that y. All right, I just take the two sides from, again, two corresponding sides. So, oops, I didn't want that. I wanted a highlighter here. I'm going to take these two sides and these two sides. And again, I'll make a proportion. So I'm going to take 7 over y and 14 over 20. You don't have to do it in this exact order, but just make sure that you're picking corresponding sides. So 7 was the left side, y was the base. Then make sure when you go to the similar triangle, you do the left side on top and the base on the bottom. So now I cross multiply. 14 times y is 14y. 7 times 20 is 140. And I divide by 14, and y equals 10. Okay, now you might have noticed that this side right here, AC, matches up to this side, all right, that it was just twice as big. So that scale factor is just 2. So I technically could have just multiplied each side by 2, like 8 times 2, and I get 16, and then 20 divided by 2, and I get 10. Okay, so in this particular case, you could have done that without setting up the proportion, but almost all of our problems are not going to go in evenly like that, and you will have to set up a proportion. All right, so given that dilation of ABC, that would guarantee that its image A prime, B prime, C prime is congruent to DEF. How do you know it is congruent? So if we dilated triangle ABC, which is the smaller one, by a scale factor of 2, its image, triangle A prime, B prime, C prime, would be congruent to triangle DEF. We know that because all of those sides were were twice as big. So if I dilated ABC by 2, then the image A prime, B prime, C prime would be 14, 16, and 20, and all the sides and all the angles would be congruent. Okay, so this gives rise to our definition of similarity, which we have right here. So similarity is similar to the congruence one. In congruence one, there had to be a rigid motion that would map one triangle onto the other. For similarity transformations, two geometric figures are similar if there exists a similarity transformation that will map one figure onto the other. This transformation can be just a dilation, or it could be a dilation with other rigid motions like reflections, rotations, and translations. All right, but to be similar, there has to be a similarity transformation that maps one figure onto the other. And the transformations can be dilations, or they could be plus all the other rigid motions that we have. So, given triangle ABC and triangle DEF, they are similar to each other, and you can see that the congruent angles, the angles that are corresponding, are matching up to each other. We're not going to use the tracing paper, but we want to be as specific as possible to say what similarity transformation would map ABC onto DEF. So here's what we first have to do. We have to get them so they're touching. So I'm going to translate triangle ABC so that A maps to D. Okay, so I'm going to translate it. A is going to map to D. So now my new triangle, okay, is going to be up here. So I'm going to have A up here, so they'll now be touching, okay, and I can call that A prime. And then I'm just going to draw something that looks somewhat similar to that other one. Doesn't have to be exact. All right, so I'm going to translate the whole triangle so that A maps to D. And I drew it so you can see it, okay? Now, I'm trying to map this onto the other. Now I'm going to, after I translate it, I'm going to have to rotate it. So I want to rotate it. I'm going to rotate triangle A prime, B prime, C prime so that A prime, B prime lies on top of DE. All right, so I'm going to rotate it, and now it's going to be down here so that A prime, B prime is going to grab a different color. A prime, B prime is now going to be here. A prime, B prime, okay? And there is my C. And then after I do that, I would have to dilate it. So I'm going to get the other color. So I rotate it so that A prime, B prime lies on top of DE. And then I'm going to dilate it. I always want to say what's the center of dilation. Dilate triangle A double prime, B double prime, C double prime using center at D and scale factor. Now I don't have actual numbers, but that's okay. My scale factor is going to be DE over AB, image over pre-image. DE is what I want it to be, and the pre-image is AB, what it was. All right, so that's pretty much how these work. Let's try some more because these are definitely tough. So in the following diagram, it is known that BCN and ACM and triangle ABC is similar to MNC. Give a similarity transformation that would map triangle ABC onto triangle MNC. All right, so they're already touching, so I don't need to worry about that. But I would then want to rotate it about some point. Well, actually, I was going to do this. Sorry, I said the word already, but think about, you have to blank about point blank, and then I want to say how many degrees you're going to do that. Then you have to blank about center blank scale factor blank. So just what we did before. Before we translated it, we rotated it, we dilated it till they were the same size. They're already touching, so I don't need to translate it. But what I'm going to have to do is I'm going to have to rotate it. Now, what point am I rotating it about? I'm trying to map ABC onto triangle MNC. All right, so I'm going to rotate it. The point that's not moving is point C. How many degrees am I going to rotate it? I can be specific in this one because I know that BCN and ACM are lines, so I'm actually going to rotate it 180 degrees. All right, then I'm going to dilate it. I need that center of dilation. The center of dilation again is going to be point C. And the scale factor is going to be image over preimage. And it's going to be CM over AC. All right, so they're kind of tough when you don't have points for them. Exercise 4, I have some points. That's going to be a little bit easier. So given triangle ABC similar to DEF on the grid below, what does the scaling factor need to dilate ABC so that it is congruent to DEF? All right, so I want to know, how did I go from, oops, I don't know what I did right there. Let's try and get rid of that. How do I go from AB now wants to be DE? It doesn't matter which side you use because all sides have the same scale factor. All right, so just make sure you're picking a side where you can count the length. Like I would not want to use AC or DF because I can't count the length, but I could use either AB and DE, or I could use BC and FE because both of those I can count the length. So K is my scale factor. Remember, it's image over preimage. So my image is going to be DE, my preimage is going to be AB, and I'm just going to count. So DE, 1, 2, 3, 4, 5, 6. AB is 1, 2, 3, 4, and I can reduce that. So that's my scale factor, 3 over 2. So it's basically 1.5 times as big. Now I want to specify a similarity transformation that would map ABC onto DEF. Well, hopefully you guys can see that I have to reflect it over. Think about what we're always reflecting it over. I'm reflecting it over the y-axis, okay, because if I've reflected over the y-axis, it's now going to be sitting here. Okay, and then after I reflect it, just so you could see, so this was my original, I reflected, so it's now sitting here. And then after I reflect it over the y-axis, I'm going to have to translate it up 4. Now, why did I say up 4? And then dilate it with center at E. Now, do they say I had to dilate it with center at E? It doesn't say I have to dilate it with center at E. So I don't see why I can't just dilate it center at F of 3/2 or 1.5. Okay? All right, and this last one right here in the diagram below, A, B, and C are collinear, and ADF are collinear. It's also known that BD is parallel to CE. So BD is parallel to CE. Give a dilation that would map ABD, which is the smaller triangle, onto ACE, which is the larger triangle. So they're already touching at A. They share A. So using a center at A and a scale factor. Remember, my scale factor is always image over preimage. So a scale factor of K. Image is going to be what it becomes, AC, and the preimage is what it was. And again, that's not, I could have said CE over BD, right? Or I could have said AE over AD, as long as it's image over preimage. All right, and the last question right here, circle the proportion that is incorrect based on the fact that my triangles are similar to each other. So the first one says AC over AB. All right, so AC, you're going to have to go through each one of these. AC is this whole left side over AB, which is the top left. And then it says CE, which is the base, over BD, which is this base. right? So oh, and I'm looking for incorrect. That's okay because that's consistent, so that one works. I'm looking for incorrect. So I got the whole side on top, and I got the CE, which is the base of the bigger triangle, on the bottom, and then I have the left side and the base of the smaller triangle. So everything matches up. These are all corresponding perfect. All right, second one. So as I'm testing each of these out right here, all right? So second one says that angle A over angle ABD, which is right there, and angle A, which is right here, over angle ACE. All right, so that's also okay. Nothing wrong with that. All right, let's look at the next one. Next one says AD, which is this right-hand side from the smaller triangle, over AE, which is the whole right side from the big triangle, equals AC, which is the whole side. All right, that is no good. So AD is from the smaller triangle and AC is from the bigger triangle. So no good, not correct. You have to make sure you're picking corresponding. All right, and we'll practice.